Hello, good afternoon, or good evening, or good morning. This is Mr. Azad, and I'm doing a recording of the lesson that was done October 8th and October 7th, right? It covers those 2 days. So before we get fully into the lesson, a couple of notices. The second version of our quiz has been posted onto every single class. It is optional. Take it if you want to earn a better score on your quiz grade. If you're satisfied with the original quiz score, no need to take it. The quiz will essentially be the same thing as the first one. Numbers have been changed. Some words have been reversed, right? Instead of increase, you might get decrease, that kind of stuff. So just be aware of that. Okay, so last time we started on these notes on physical and chemical changes. So if you haven't done that yet, make sure you copy it into your evidence notebook. And as far as periods 2, 4, and 6 go, I answered 1, 2, and 5. So that's where I'm going to start off today. So apologies if we are covering something you're already familiar with, namely numbers 3 and 4. So in these sets of notes, we have a slideshow to go along with it. It's not week 4, it's actually week 8, so that has to be changed, but the point still stands. We're going to be using that presentation to kind of guide us here. And so for number 3, where I asked, what are some examples of density, conductivity, magnetism, and solubility, and what do these properties have in common? Well, I will first start off with the fact that, hold on here, these are all physical properties, right? Density, conductivity, magnetism, solubility, these are all things that are the property of a given object. So let's take a look at our presentation here. So density, the mass over the volume, right? And it's basically whether or not something's heavy. Will it sink? Will it float? You base it off the density. And so based on the material you get, it will have density. And so if I took a piece of iron, let's say, or steel, I have a piece of steel, right? This steel would have the same density as another piece of steel, right? A smaller piece. Same thing though, equivalent. And so these properties all kind of share that general pattern. Conductivity, how much heat or electricity or sound a substance could move through it. And so if I try to get some electricity and conduct it through this steel, it will be the same as this thing, right? The only difference here is size. Magnetism, right? These are metal. They'd both be attracted pretty equivalently. Solubility, steel doesn't really dissolve very readily, but if I got something like table salt, it would dissolve pretty readily in water, right? Solubility is just how well something dissolves. And so these are all physical properties. Steel and pieces of steel would have the same densities, conductivities, magnetics, and solubilities. So as per usual, let's just highlight that orange, real colored up. And so what is a physical property then? If it's all these things, what is the commonality there? The commonality is that a physical property is something that can be measured without changing the identity of that matter, of that object. So if you're trying to take something size or get its shape, those are all physical properties. So it's a property that can be measured or observed without changing the matter slash object identity, right? And so you could measure the density of an object without needing to do a chemical reaction for it. You can measure the conductivity of titanium before needing to change what that object is. So these are all properties that you don't need to really mess around with. You can just measure it, observe it, and the matter can stay the same. Previously, we'd already answered what is the law of conservation of matter, and just to repeat myself, matter, like energy, cannot be created or destroyed. You can only transform it from one thing to another. And so we're brought to states of matter. What are the states of matter? We're talking about 5 of them. So most commonly, you'll know about solids, right? Your typical things, most things you could hold. It's got a definite shape, it's got a definite volume. So that's a solid. You got liquids. These things take the shape of their containers. You've got gases. Uh, no fixed volume, no fixed shape for the container. And then you might have heard of plasma, right? The stuff lightning bolts are made out of. Basically, a highly energized stream of particles. And so if we look at the presentation, the next slide, not the conservation of matter, this one, you get a pretty good demonstration of what solids and plasmas all look like. So solids are very crystalline. All solids pretty much share that pattern where they're nice and organized. Those blocks are right on top of each other. Those particles are right on top of each other, and they don't really move. A liquid, a little bit more flowy, right? The bonds between these particles have been disrupted. They're a little bit more energized, and so they kind of flow around. And gases, the bonds between those particles have been completely broken down, and so they're kind of free and highly mobile. Plasmas, even more so, right? You take a plasma and you pretty much just energize it all the way to the point where the molecules start to break down, and you're looking at just a mix of electrons and particles just kind of flowing around. Ions is what you would call them. But if you go the opposite way, right? If you go the opposite way, you cool things down, you'll eventually get to something called a Bose-Einstein condensate. Bose is an Indian mathematician. Einstein, you know who Einstein is. And so a condensate is typically a supercooled material, right? It is a material that has reached around absolute zero, and it's typically called the 5th state of matter. It was discovered in 1995, and we have been making inroads with that as we've gone along. So I really like this question because it tells us that even something as simple as states of matter are growing and expanding, right? We could push the boundaries of something as easy as what are the states of matter. Typically you would think 3, but in reality there's 4, there's 5. There's actually a lot of different types of matter. And so these are boundaries we're always pushing. And so plasma, right? Condensates, these are really cool boundaries that science keeps pushing, and it's nice to know, right? Science is an evolving subject. I like to throw up this picture up here because it's such a good image of the technology that's involved here, the cooperation needed, right? We have CERN and their Large Hadron Collider, which is essentially a massive particle accelerator that, you know, you collide with, right? Other particles are collided here. And they're responsible for a number of scientific discoveries, right? A huge undertaking, a 27-kilometer mile or diameter tunnel built solely to collide particles with each other. And in the future, they're thinking about increasing that size. So this kind of engineering and science takes the minds of thousands of people working together, and we're pushing those boundaries. It is absolutely incredible. But to go back to it, get back to our assignment here, our notes. Condensates are our 5th type of matter, and it's just here mostly to round out the states of matter. Now, for number 7, we're talking about the particles in water, steam, and ice. How are they arranged? Well, you just want to be able to draw something similar to this. And so use the draw feature in Google Docs to show what you think. So let's go ahead and channel our inner Bob Ross. Let's go to Insert. We'll go to inserting a drawing, new drawing, yes. And to channel our inner Bob Ross, we want to start off with a nice canvas. We go ahead and make a rectangle, and our canvas, I want it to be, let's say gold. Gold is a great color for a canvas. Inside that canvas, we're going to have some squares to show off our solid, liquid, and gas, our ice, water, and steam. So we're going to have those right there. There we go. We've got, there we go. We got nice jars here. We're going to throw our particles in there. We'll throw our particles up as circles. And I like my ice and water to be bright blue. So these are our particles. As a particle of ice would go, we're going to have it be nice and organized, nice and crystalline, very ordered. Just 4, not too many. And so when it melts, it starts to kind of collapse in on itself. We'll have most of them be lined up. We also see some overlap occasionally. So we get a nice little floor of water. And when it turns into steam, we're going to see a lot of it just kind of turn into particles. We'll have these things be floating. And there we go. That's it. So when you're satisfied with your drawing, just Control C it. Another way to do this, if you are not as artistic as Bob Ross, just go to Image and search the web. We're going to search the web. We're going to type in matter. It's already been done. Pick the first image there. We're just going to insert it. Done deal. Great. And so we're set to move on. These notes will take a little bit less time than the class period, mostly because I'm not getting nearly as off topic as I do. I get really excited when I start talking about the states of matter. So a chemical property. What is a chemical property? Well, it's not a physical property. It's kind of the opposite. So it's a property that can be measured and observed, but you have to change the matter/object's identity. So let's take a look at the presentation. What is a chemical property? It's a property that is observed when a substance changes its identity. A property that is observed when a substance changes its identity. Fantastic. And there's a list of observations that can be made for when an object changes its identity, and we'll talk about that right now. How do you know a chemical change occurred? This is arguably one of the more important things you'll figure out this year in chemistry, and it's the signs of a chemical reaction. And so a change of color, right? That's our first sign of a chemical reaction. A change of color, think about a nail rusting, that's why it's orange. If a nail rusts, the oxygen in the air has reacted with our nail to make iron oxide, and so we get an orange color all around it. Same deal with copper. If you leave copper out next to some seawater, like the Statue of Liberty, it'll go from brown to green, right? Nice little cerulean green. Other things that change color when you chemically react them. Cooking food, right? Think of a steak. It turns nice and brown after you've cooked it up. And so we got changes of color. A change in odor. This one most closely relates to production of gas. But if you smell something new whenever you mix two chemicals together, you know you've had a reaction. If you go out for a run and you come back all sweaty and smelly, you'll know you've done chemical reactions on your body. Your body's working to cool itself off, and it's doing this through a host of chemical reactions. Production of new gases or vapor. Well, if you try to cool yourself off with some Coke or some Sprite, you'll hear a little when you open up the soda bottle. And so that there is the carbon dioxide releasing itself, right? You'll see those fizzies and bubbles, right? So you get a production of new gas. The input or release of energy, if you blow up some dynamite, you know for sure that is a chemical reaction, and it's the release of energy that gives it away. If you cook some food, if you cook an egg, the egg changes color. It goes from clear to white, yellow to like orange. And so that's one way. But you've also put in energy into the egg, right? You've put in that thermal energy to cook your egg. And finally, chemical reactions are difficult to reverse. Not impossible. Nothing, never say impossible when it comes to science, but um, difficult to reverse, right? You'd be very hard pressed to uncook an egg or unblow up some dynamite. It's very hard to reverse a chemical reaction. And so let's go ahead and list these out. The change in color, change in odor, a production of gases, the input or output of energy, and finally the difficulty in reversing change. Those are our 5 ways we know chemical reactions have occurred. And so for number 10, we're going to just go through and list whether or not these are chemical or physical properties. If you want to do it yourself and just wait for me, I'm going to do a countdown for 5 seconds. And as I'm counting down, just pause the video, attempt it yourself, and we'll go through and answer it. So 5, 4, 3, 2, 1, done. All right, let's go through each of these. A piece of sodium fizzes and makes bubbles when put into water. Well, we should know at this point, if you're fizzing and you're making bubbles, you have some gas being made. If you have some gas being made, it is a chemical change. Table salt is put into water and dissolves. Remember, solubility. If something is able to dissolve in water, you could undo that. That's a physical property. If I wanted to get my table salt back from the water, all I have to do is boil the water off and collect my salt. And so this here is a physical change. Water becoming ice, you know for certain that this is a physical change. Iron is starting to rust. I've used that example previously. It's a chemical change. And a glass plate is put into a microwave and shatters. At the end of the day, that glass plate is still made out of glass, so nothing's really changed. It is a physical change. Let's go ahead and set these up in orange. And so we're set. And now that will pretty much cover us for our notes. And we'll be starting with assignment 5, either on Friday or Monday, depending on what period you're in. I would like to have a side conversation about statues for a second and the chemical reactions that appear with these guys. Most statues are covered with a layer of varnish, yes, to protect them from the elements, but also to protect them from people. Now, you'll notice here that this statue is covered in a layer of varnish, but some people think it is a symbol of luck to be able to touch the nose of the dog. And so hundreds of people, thousands of people will touch the nose of the dog, and you see the evidence of that, right? The dog's nose is shiny. Why this happens is because your skin is covered in a layer of oils and grease that kind of wears away at the varnish. And people have a tendency to touch dogs for some reason, statues of dogs. As you'll see, their noses, their paws. My favorite one here is to give this statue a belly rub. It's a fun set of things. People seem to love dogs. So just be aware whenever you go to a museum, don't be touching, the exhibits because it does damage them as time goes on. I think people love to give this guy belly rubs or ear scratches. All right, and so that will take us to the end of today's lesson. I hope you all learned something new. If not, I hope you at least enjoyed this. All right, I'll see you all later. Bye-bye.